Hello everyone, welcome to the tutorial which is a follow-up on the parametric surfaces and parametric curves. Today I will show you how to model something like that. This is a building by Felix Candela, Palacio de los Deportes. I don't know if I pronounce it correctly. Anyway, this is a roof for a stadium, probably, something like that. And I will show you a simplified version of this model, however still working. By the way, this is a finished script, and the first thing that you should notice is color coding. I told you about it, I believe, during the first tutorial. I told you that groups with different, let's say, meaning should have different colors. So my way of doing that is whenever I have input components, I color code the group as blue. Regular procedures are just gray. The final output is red, and anything that is related to preview should be yellow. At least in my scripts. You can have your own color code. However, it is necessary that you follow the same logic everywhere. And unfortunately, you are not composing a piece of art here. So, you should prioritize usefulness of this color code instead of using different shades of pink. However, I also appreciate something like that when you submit your scripts, but in professional work, unfortunately you have to be professional. Okay, so what is this script about? Basically, we have a piece of a sphere. Actually, I don't think that we will have a piece of a sphere. It resembles a piece of a sphere. It bases, okay, so it will be an ellipsoid. If we look from the top, then you will notice that actually the base is a rectangle. You can control the dimensions of this rectangle. You can also control the height of the whole structure. However, this is not a direct control. I'm controlling just the arcs using this slider, those arcs that build up the surface. Then the number of divisions. You cannot see right now where those divisions are because the surface is divided, but it's still flat. And we can control those spikes, let's say. As I said, this is not accurate because here in Palacio de los Deportes, all those panels, all those modules, they are built up kind of differently from what I did. So in my example, we just have a rectangle and then a vertex, and I create these kind of pyramids, while the real structure is more complex. We have a rectangle as a base, but we have edges which are touching the middle points of the segments of the rectangle as the base, and they are created like that. And this is a little bit more complex to achieve. Probably maybe we will extend this tutorial just to show you how to achieve this exact effect. However, yeah, we'll create something like that. I will also show you once again probably how to use shaders from your file to achieve this kind of nice rendered look straight out from Grasshopper. So maybe you want to you will use that for simple animations that take 10% of effort but can make up 90% of the appearance of your project, let's say, for presentation. Okay, let's start from a new script. So I will open new Rhino right now. Okay, and now how do we start? So I will start with a rectangle, which is the base, and what would I like to control here? Probably length and width of the rectangle. So I will preserve those two parameters. Then I will find center points or middle points of the segments of the rectangle. I will move them up and then create arcs through every triplet of points that I get, like that. And after I have, and when I have those arcs, it is quite easy. Actually, there is one component that creates a surface using such four such four boundary edges. So let's start with a rectangle. There is a component called rectangle, no surprise here, and we need two parameters, x size and y size. Let's put them here. I won't put labels because it's obvious what those numbers mean. So here values, a number slider. So I will use a number slider between 20 and 50 meters, just to have a certain amount of control. Input those values here, and here we are. So we have a control over a rectangle. And now let's use that to create let's extract only the segments, because we will use those segments into other groups. So explode command. This command, I would use this command normally in Rhino if I'd like to extract the segments of a polygon. So explode, and I get the segments. And I wouldn't normally make groups out of such, small pieces of code. However, for our purposes, as long as we are not advanced enough, I will do it. So I would group that now and call that get base segments, maybe. So I'm following the logic of having groups that have some input, do something, and have a meaningful output. And they also should have meaningful names, like get base segments. And these segments are those lines here, those 4 lines. And now I want to build arc upon them. So normally if we were in class, I would ask you to do it on your own, because we already did something like that. We had we did scripts where we had lines that laid straight, that laid flat on a plane, and then we used their middle points to create such arcs. But I will show it to you again. I will repeat that piece for you. So we need those segments again. And as the other parameter, we need height of the arcs. Right? We need to be able to control how tall those arcs are. So height, and let's use some sensible range here. So maybe from 1 meter to, actually it should be much larger than, 1 meter to 7 meters. And first thing, we need to find the middle points of curves. So there are 2 ways. A shorter one is just to use the curve middle component. However, when I'm normally in our computer lab, I'm using Rhino 5 because this is what we have in the computer lab, and in Rhino 5 we didn't have this kind of component, curved middle component, so I would use evaluate length just to practice the use of this component. So instead of curved middle, let's use evaluate length. As you probably remember, evaluate length gets you a point on a normalized at a normalized length. Normalized means from 0 to 1, so 0.5 should give us curved middle. So evaluate length 0.5. We don't need to reparameterize here. You probably remember this term. Why? Because evaluate length doesn't operate on parametric space. It operates in a metric space, and it does a kind of reparameterization inside, inside by itself. So if we used evaluate curve, which takes a parameter, then we would need to reparameterize the curve. So evaluate length, we get middle points. Now we need to move them up. By default, many components have some default values, like for instance move has a default vector of 0, 0, 10, but we want to create our own. A simple way to create a straight vertical vector is to use the unit Z component. It's very fast to put on the canvas because you just need to type in the name of the axis along which you want to create the vector. So Z stands for the Z vector, X is for unit X, and Y is for unit Y. So it gives you, it's very fast. Factor determines how long the vector will be, which means how far you will translate the point, or any other geometry, of course. Okay, so this is the output. I will increase the value here. And what next? You probably remember from one of the previous classes that we can create an arc from 3 points like that. We need point A, B, and C, and we would get a nice arc going through these 3 points. Where A and C are the endpoints of the segments. So we need to find endpoints of all these segments, which is again quite easy. We will just use the endpoints components from which we get start and end of each of those. So start would be A, let's say, that moved point would be B, and the end of each segment would be C. Let's see if we have the component arc 3 points. Yes, so A, the moved one is B, and the endpoint of the segment is C. Looks nice. Okay, so now I can control the shape, at least how I imagine that. I can control how flat it is. This is exactly what I wanted. All right, so let's call that a group. Once again, we input something, we input segments. We input a desired height, and we get arcs, whatever that means, on the output of this group. And select all the components, Control plus spacebar, plus, of course, Control plus spacebar gives you that handy radial menu with which you can quickly group components. Of course you could, I suppose, but I'm not using that too often. You can use a shortcut Ctrl plus G. Let's try it out. Yes, so Ctrl plus G will group components, and Ctrl plus Shift plus G ungroups components. And maybe an important remark here. No nested groups. Which means that you should never put a group inside another group. Of course, again, this is just my style and my preference. Some people may have different preferences. You may hear different opinions from other, programmers, computational designers, whatever you call them. So you just have to follow those that you feel the most, right? So you need to like way of working in Grasshopper, and the things that we say are just advices. So yeah, you can follow them or not, but I really recommend that you don't nest groups, because it is actually first it's reducing the clarity of your scripts, and also such scripts are more difficult to later modify. Okay, now let's create a surface from those arcs. Yeah. Okay, this one will be not tricky, but I will show you one component which is not in the scope of today's meeting, which is called list item. The reason why I will use this component is because I need to have a proper input to another component which is called edge surface, which will allow me to create this nice spherical shape. I just need to input those 4 arcs as curve A, B, C, and D, but here I have them all on a single list. So I couldn't simply input them like that, because I need them separately. And this is why I will use list item. This is a kind of it may be used as an explode component, let's say, which will input different items to different handles. You need to zoom into this component, and you will see small icons. I don't know how it is called. It's probably something like dynamic GUI, dynamic graphic user interface, and it allows you to add other outputs. This is a property of some components. Not all components have that, but some have, and this is very useful. At least for in general, it is very useful. We will use this for our purpose, which is to explode the list into 4 separate elements, and you should get something like that. Edge surface is quite a smart component, and should give you all a nice output. What is very important for us and for you whenever you will try to tessellate a surface is that you operate on untrimmed surfaces. I think that I told you about trimmed and untrimmed surfaces the last time during the last tutorial. This is very, very important to have, whenever it is possible, work on untrimmed surfaces. It will be much easier for you to tessellate, to create patterns on such surfaces, etc. So edge surface is a nice component because it often gives us an untrimmed surface, and also it is nice. Let's say it's parametrically quite even. Probably in the future you will understand what I meant when I told you parametrically even. But let's leave that for now. Anyway, we have an untrimmed surface. And I would like to do, what I would like to do with it is something that I showed you the last time, which was when I had the surface, I split it into smaller, into subsurfaces, just like that. So I will create separate elements. And this procedure is called tessellation. And I will fully tessellate this surface. For that, I will use the isotrim components, which takes a surface. So we have a surface here. And it also takes domains, subsets. I hope that you remember this topic from my previous explanations, because I won't explain it too much right now. What we need to do is we need to construct a domain, two-dimensional domain. Actually, honestly, we don't need to do it, but I will show you some shortcuts later, tips, tricks, whatever. Let's do everything now as it should be done. So we construct a domain which is a normalized domain from 0 to 1, from 0 to 1 in both directions. Once again, you probably remember that we have that every surface has two directions like U and V, which are corresponding to with X and Y, but in the world of this surface. So U and V are just directions like X and Y, but bent on a surface. So we have a domain here, and now we can divide the domain again with that square symbol, which stands for two-dimensional. And we need number of segments as the input here. So integer and a slider. Let's say from 4 to 12. Doesn't matter that much. I will use the same value for both U and V because I want this tessellation to be as even as possible. And I put segments here. Normally I would ask you what is wrong, why I just get this tiny piece of surface as an output here. But yeah, I cannot get any answer from you right now. So maybe just a second for you. You can pause here and just think on your own and try to find a solution. You will learn and memorize everything much better if you do it right now. But if you didn't, I will tell you. So, to remind you, every surface has its own parametric space. This one specifically has in both directions the same value, the same range of parameters from 0 to 52. And I'm extracting subsets between 0 and 1, which just gives me this tiny piece of the larger parametric space. So there are two ways that I can, two things that I can do. I can either divide this domain, which is precisely the domain of this surface, and just those segments will be larger and will cover the whole parametric span of the surface, or preferably, I could do something different. I could just reparameterize the surface. Maybe I will reparameterize it here. It's not possible, this component. Okay, that's interesting. So I'll reparameterize it in isotrim. And I will emphasize this for you. And will work just fine. Why? Because the parametric space, parametric domain of the surface after reparameterization ends up as from 0 to 1 in both directions. So this default domain will be valid in this case. Okay, now we have the smaller pieces. you can notice that whenever I'm finishing a group, like in this case, I'm turning off the preview of everything that is not the output, and I leave just the, what is important. So I leave just, in this case, the surfaces at the end. And I also recommend you do that to avoid cluttered viewports in Rhino with too much information. Okay, next step. Let's create pillars maybe underneath those arcs. So we need an idea for that. So we have straight segments at the bottom, and we have the arcs like that. And now I would like that if those arcs were connected exactly at the seam where those segments, sub-segments of the main surface are joined together. In order to do that, I would need to divide the arc in exactly the same number of segments as I divided the surface. Right? If it's divided into 4 pieces at the top, then I would need to divide the arc as well into 4 pieces, and do the same with the bottom segment. And then if I have something like that, I can simply connect those like that. Let's not get into the issues of building trusses in here, because it's more complex than it looks like. So it's also not the topic for today. But once again, we need to divide the arc and divide the bottom in the same number of elements as the main surface, and then just connect them. So what do we need? We need the arcs. We have the arcs here. And we need the segments, which we have here. Get base segments. Okay. We have the arcs and the straight segments. And we need the number of divisions. Which is exactly the same as this number of divisions in create tiles group. Now 2 times divide curve, and connect the outcome with lines. Of course, this will be not perfect, but for our purposes, I think that this is enough. Again, turn off the preview. Group everything together and give it a name. Create pillars. We have, okay. So we have pillars, we have tiles, and now the last step, create the spikes on the tiles. So for every tile, and this is a kind of algorithmic terminology. I told you, I said for each tile. And now I will define a procedure that should be applied to every tile separately. Actually, we did something like that before, for instance here. So for each segment, extract endpoints, find the middle point, raise this middle point by a specific vector, and create an arc for each segment. And now for each tile, for each subsurface, I will extract the center point. I will also find the normal of the surface at that point, and I will move the point straight up. By straight up, I mean along the normal vector, and then create this kind of pyramid shape. So first find the center point. Again, I copy this component. You probably remember probably you don't remember, honestly, okay. How do we find points on a surface? We find points on curves by using evaluate curve or evaluate length, components, and surfaces. For surfaces, we use evaluate surface. And what do we need to do? We need to reparameterize. Why? Because otherwise, I will use empty slider just to show you what happens. I'm creating a UV point here between 0 and 1, and for some reason, even though I input 16 surfaces here, I get a single point. Why is that? Actually, this is not a single point. We have more than one point here, but it's hardly noticeable. But the truth is that even if those surfaces are trimmed surfaces, let's say, they are pieces of a parametric space of the larger segment. And if you look closely at their parametric space, then you will notice that they are not from 0 to 1. And whenever I pick a UV point outside of this domain, I actually pick a point beyond the surface. Maybe I will demonstrate it to you by changing those values even more. So construct point, and I will allow negative values here. And now I have a point really below or beyond the surface. Why is it possible? Because every NURBS object is just an equation, and what you see here is just an assumed continuation of what would happen if we would input different parameters to that equation. This is not a proper... Okay, this is just an analogy, so don't take this one-to-one. This is not how NURBS works precisely, but it can give you an idea. So let's say that we have a function, a cubic, square function, which looks like that more or less. But you want just a piece of it. So you limit x, for instance, to be from -half to (1.5), and you just extract this piece of the graph. However, you still have all the information required to calculate the graph's value for any value outside of this domain. Of course, sometimes for NURBS geometry, this is much more complex. It's not as simple as that. However, you can think of them as this. So what should we do here? We should reparameterize all those surfaces to change their domain to sit in range of 0 to 1. And now we can use a normal slider. Actually, we don't need sliders here because we just need a center point, which would be at 0.5 in both directions. Because right now all the domains are from 0 to 1, so 0.5 will be exactly at the center of the domain. And now we have those points, we have normal vectors, but I don't have the drawing anymore. Anyway, a normal vector if I just move points by normal vector, I will move them outside the surface. Actually, I will move them to the inside. You might get the same error. And this is because this component edge surface doesn't really know where is the top. You know, and it matters. It matters actually where the top is. So, you know, we can control that, okay, but we would need to create a few conditional statements in here. We want to avoid that. So if I would like to move this point to the outside, I would need to reverse the normal vector. And there is a component for that. I will just reverse the normal vector. Now the points are on the outside. And also, I want to change the amplitude of the vector. The amplitude, also, we can refer to it as to the length of the vector. There is also a component for that. It's called amplitude. We could also simply multiply the normal vector by some value, because normal vectors are, as the name suggests, normalized, which means that they are unit vectors. Their length is equal to 1. But let's use the amplitude component to get acquainted with more Grasshopper functionalities. And now a slider to control the shape. I intentionally set this to minus 0.10. I will show you why. But now we have the point. The point is moved, and now we want this pyramid shape. How do we do it? We use a component which is called extrude point. We have the point and we have the base. The base is, as you can read from the description, profile curve or surface. So I will input that to the surface. And here we are. Again, turn off the preview. I will zoom into that group so you can copy the components. You can pause now. Create spikes. I will call those spikes. And the type of this output is BREP. Extrusions are BREPs. And this is our final. So we have the pillars as curves, highlighted in green right now, and we have those spikes as BREPs. And this is our final output. I usually color the final geometry in red. And I think that this is all. I can control the height. Okay, sometimes probably the edge surface fails. Or, okay, yes, it fails. It actually fails to create a surface from that. It counts as a BREP for some reason. But let's not think of that for now too much. Let's limit the slider so that it will work all the time. So in my case it would be 10. So I will just limit this to 10 to make sure that it works every time. I can increase the number of divisions, and I can also control the shape here. Okay, that would be all. And for those of you that are interested in how to create a nice display straight from Grasshopper, you can stay and listen. So I changed the preview to rendered, and as you can see, the rendered preview is not really nice, just as the Grasshopper preview. You get those ghostly red geometry. But you can use a component which is called custom preview by default, and it turns your geometry into something that can be rendered actually. By default, the material is a pink something. It's pink plaster, or I don't know, pink soft plastic. So let's tweak it. Let's tweak it so it's not pink and it's not plaster. What was the color of the roof? I believe that it was copper or something. And now I will show you how you can quickly do it. I won't create a shader in Grasshopper. I will rather create a shader in my Rhino documents, and then I will import it to use in custom preview. To do that, first we need to create a material in Rhino. I think that the easiest way to do this is just to go to layers, and there you have a material column, and you need to click on one of those swatches. I will just change the material of the default layer. I will change this to metal, and then maybe rougher. Color should be gold, but reddish. It's more like copper. Okay. And yeah, here we are. Okay, nothing has changed because this material is applied to geometry which is in Rhino document and on the default layer. This is just a hypothetical geometry that can exist, but it's just something that Grasshopper simulates. So now let's use this shader in Grasshopper. You have to go to Primitive tab at the top and select shader, or just type in shader. This is a data container for shaders. Shaders are like textures, materials, whatever. Your graphics card uses shaders to change the appearance of what you see. And then you right click on the shader, choose set one material, and you get metal. You can select the material from the Rhino document. And here we are. It just looks nice. By the way, when I was preparing this tutorial, I found out that you can input something more to this shader, and actually you can take a screenshot of something. I'll just quickly take a screenshot of this. I know that this won't give any any nice result, but I will do it anyway. Or maybe, okay, I will go to top view and I will take a screenshot of all that. And then this is already in my clipboard, so it looks like a nice texture. And if you right click on shader, okay, once again, take a screenshot, copy this to clipboard. You need that in your clipboard, and then shader, set one material. Still nothing. Okay, sorry. You need to paste it in Rhino. You need to paste it in Rhino. It will be pasted as a picture frame. And now you can use it here. Okay, it doesn't look good at all. Okay. Well, but you can do that. So if you take a screenshot of some texture, we would need to tweak the UV mapping here for sure as well. But if you take a picture of something, you can paste it into Rhino, and then this will be automatically treated as a texture or a shader. And you can use this in this shader component. Okay, it doesn't make any sense, but you can do it. Okay, custom previews, select this as a group, and in my scripts I set hue 60 to color display groups, and I think that it would be all. It turned out to be quite a long tutorial, honestly, but I hope that you enjoyed that. Thank you and see you next time.